Okay, so welcome to the first of our videos for while we're away for physics. And I may reshoot this one later, but for right now, I wanted to have a chance to show some demonstrations of collisions and the different sorts of collisions that we get and how momentum conservation plays out with them. So as a reminder, we have for our definition for momentum, that is mass times velocity. In the olden days of Newton, this was the quantity of motion that is a thing that shows up in the Principia. And we find that it's one of these properties that is conserved through any and all interactions throughout the universe, really. So all of our conservation laws, whether it's momentum or energy, angular momentum, electric charge, they all are some of our fundamental rules describing the behavior of nature. And with momentum, with any of the conservation laws, the total amount of the thing remains the same regardless of any other changes that may take place. So you can total it up before those changes, and then you can total it up again after those changes. They'll be the same value. So it can be passed from one thing to another, but you can't make more of it, you can't get rid of it. And the little arrows above mean that it's a vector quantity, which means direction matters too. And although in the examples we're going to show here, all of the motion, all of the momentum is going to be confined to one dimension, just back and forth on the track below. And we're going to take a look at that with these carts here. So these carts have fairly low friction bearings on them, which means they can coast along with very little acceleration and very little change in velocity until I do something with my hand. So this is a feature that will isolate them from the rest of the world for the most part, at least as much as we care to look at. We can say that they comprise a closed system. And in closed systems, then there's no outside interference. The momentum that we're looking at isn't leaking off into the outside, and it's not coming in from the outside. So we can take a look at this and collide these things. Let's see. Okay, we'll try this version. These two carts are approximately the same mass. And so this means that if one was going one speed and the other was going, then the other one, if it were to be going the same speed and direction, would have the same momentum, since their masses are the same, approximately. So we take a look here, and inside these guys there are little magnets that are lined up just so that they can repel each other. So we can have a collision without the surfaces colliding, without the surfaces pushing against each other. And this will allow the less of the energy involved in the collision to be transformed into other forms. It'll allow the momentum to mostly stay in the form of the bulk motion of the object, and the energy to be confined to that form as well, rather than into any sort of thermal energy, additional thermal energy. Anyway, here we go. So let's go ahead and launch this thing. So we'll give it a light shove. And we see that the earlier one that was stationary begins to move during the collision with approximately the same speed and velocity as the one that was initially moving. So we can do this the other direction. And again, all the momentum was passed from the one object to the other, but it's the same momentum as we had before. So momentum here gets to be conserved. This particular type of collision is known as an elastic collision because most of the energy, well, all of the energy that was in the form of kinetic energy, energy of motion, before the interaction, before that magnetic force began to act on these, returns to energy of motion, kinetic energy, after the interaction is complete. This is a very bouncy interaction. And in our class, we haven't been looking in detail at the mathematics involved in energy yet. And so I won't go into how the math works out precisely here. But it does make it so that the one car gets to stop and all the momentum passes into the other. Now there's other ways in which these things can interact and collide. We've got little Velcro pads on these as well, and so these can collide and touch and stick together at the end of the collision. So in that case, since they've got each have their own mass that's about the same, this is going to make it so that the momentum gets distributed between both of them evenly. Their final velocity between each other will be the same. Write this down here. So an inelastic collision So, as I was saying before, with an inelastic collision, they'll stick together, and so that will mean that their final velocity will be the same for both carts. And since before the momentum was confined to one cart with just one of these masses, but it has to be spread across twice the mass at the end of the collision, that final velocity will wind up being half the speed. So let's see how that plays out. So we go ahead and give it a launch, and we do see they're moving notably slower here. So that's sort of our basic differences between our elastic and inelastic collisions for appearance. Let's play around a little bit and see what happens when we vary the masses. So if we go ahead and let's stay with the inelastic collisions for the moment, and we'll add a bit of mass here to the moving one. And so if we do that, then there's going to be a lot of momentum per unit mass in our moving object here. What do you think is going to happen for the final speed at the end of the collision compared to our earlier version where the mass was evenly distributed between the moving and motionless cart? Let's find out. So it slows, but not a lot. I'll do that again with a higher initial speed, just for comparison. So a small slowing down, but not a great deal. Let's make the target car the more massive one now. So now, in order to have the same velocity in this more massive target car as the lower mass one, more of the momentum is going to have to be in the massive car, and so we may expect that it's going to move more slowly compared to the version where the mass is evenly distributed. Let's find out. So there you go. Now let's try again, playing with the mass variation, if we have a more elastic collision. So we can start off, let's say, with most of the momentum in the moving car, and let's see what happens when we collide them in a more elastic way. All of that momentum had to continue going to my left, your right, and so to do that, the formerly stationary cart had to move pretty fast. Now if we go and do the same sort of collision, but now have our stationary cart be very massive, what will happen? Let's try and find out. So, the originally moving car, the low mass car, was able to bounce backwards, have negative momentum, and still, because so much mass was moving in the original direction of motion, it compensated. That was enough. Momentum going that way minus the momentum going the other way to make the total momentum still stay the same. So that's where we're going to end for the now, and I will see you another time.